So let's consider a big rectangle. Something that is maybe 6 meters by 4 meters. And the whole thing has a mass of, I don't know, 96 kilograms. I'm going to cut a corner off that is 1 by 1.5 meters. What is the mass of this corner? So I can pick any of you, and you're going to be okay with it? Jay, how do I do it? I'd like to know how you did it, because there's a little bit more nuance here, right? Just a little bit. You divided 1.5 by 24 and then multiplied by 96. Okay. Right? So just to rearrange this a little bit, because his answer will be correct, I'm going to rearrange it a little bit. I'm going to just do simple rules of algebra, okay? First rule, I'm going to switch these two because I can multiply in any order. Is that okay? So I have 96 divided by 24 times 1.5 equals mass. I'm going to divide both sides by 1.5. So I can divide both sides of an equation by the same thing. So, and again, I'm doing this purposely because this is the mass to area ratio on the left. 24 is the area of the whole piece. 1.5 is the area of the corner. This would be the surface or areal density of this rectangle. And so we took the density and used it to figure out the mass of a piece. Now, I don't know what thought process Jay actually used to come up with his calculation, but it is the same idea as the ratio of the whole is to a ratio of a piece. Everybody follow so far? All right. I need that. I need this understanding of this density idea, because that's what this is for what we're going to do here in a minute. I don't believe I have to do another example. I think we're good. You've done examples of volume in chemistry, and it was either kilograms per liter, or it was kilograms per cubic meter, or it was grams per cubic centimeter, grams per cc, grams per milliliter. Any of that ringing a bell from chemistry? It should, but I don't know that you remember that far back, but you did these problems in chemistry. I want to talk about the moment of inertia of the bar, the meter stick. If we think back to yesterday, the activity I asked you to do for homework, many of you got the right answer. Something like 3, 3, 25m when you broke it up into 10 pieces, or 3331m when you broke it up into 20 pieces. Do these two numbers look familiar to you? They should, because they were probably the right answers. Now, you might have done them in terms of L. You might have done them in terms of centimeters. Across the course of classes, we did several different ways, but I'm expecting that to 3 decimal places, we should be getting an answer that looks like there's a lot of 3s in it, right? If I reduce this to 3 decimal places, a lot of 3s, I'm expecting my moment of inertia to have that as part of the way it should look. Because we did estimates, and we know that these estimates are a little bit small, they're not going to be that much different. So let's see what the actual moment of inertia comes out to. But I don't want this to be the moment of inertia of a specific object. I want to show you how to take the moment of inertia of an object of mass m that is length L. Now, of course, to actually do this, I need to choose where my axis of rotation is going to be for this calculation. Because we know the object can have multiple moments of inertia depending on the axis of rotation. We're going to do this about the end. Now, there are some steps to doing this process. I'm not going to write step 1, step 2, step 3, step 4. I'm going to say to you the steps. Now, the first step is to recognize that just like when we did this before, when we did this as an estimate, we broke the object up into individual pieces. I want to do that again, but I don't want to specify the size of the piece the same way. So I'm just going to choose somewhere on my object and draw a square to indicate that this is the piece of the object that I'm going to be looking at for my demonstration. This is a piece of mass. I like saying piece of mass. It sounds like you're saying something else. So when I refer to my piece of mass, remember, we're talking about physics. I still say that a piece of mass t-shirt has great potential because it's clearly talking about physics. You put some moment of inertia stuff on there and all that, and refer to looking for a piece of mass on campus. I think we really have the double entendre we're searching for, but it might cross the line a little bit. I mean, it's going to go on YouTube, and that's okay. But this small box represents the piece of mass that we're going to be observing. Now, the reason we use calculus is calculus allows us to do something that we can't do with algebra. With algebra, the problem we have is that this side of our piece is closer to the axis of rotation than this side of our piece. So no matter what size we make our object, we know it's an estimate. We need our piece to be so small that the difference between those two really vanishes. And that's the magic of calculus. That's what the integral will do. But up until that point, we're going to treat this piece as if it's big enough to be observable. And we're going to give it some dimensions. Now, the first thing, bless you, the first thing I want to recognize is that this object itself has a certain symmetry that suggests I can treat it like a long, skinny object, meaning I'm going to use one-dimensional symmetry on it. Does everyone understand why I'm going to do that? If not, is there any reason why something on this side of the object would be different than this side of the object? Because of that, that's what allows me to treat it one-dimensionally. Because the top and bottom of the object aren't contributing in any meaningful way to the moment of inertia. If the top and bottom of the object did, then I wouldn't be able to do what I'm doing here. So I'm going to treat it with one-dimensional symmetry. The first thing I want to do is remind you that we are working from this formula for moment of inertia, but we're going to use the integral formula. the one that allows us to make our pieces very small. The integral formula still preserves the r squared, but changes m to dm. Now, the introduction of d is not introducing a new variable. The d here is a calculus construct. It actually means piece of mass. It's the calculus version of delta. And it's there to remind us that this is a very small piece of the mass. Now, what we have to do is we need to assemble something here that we can take the integral of. Right now, this current expression is not descriptive enough. We can't integrate dm because where each piece of mass is on the object matters. So there's no integral that can be done here. We have to figure out how to write this so that it describes where each piece of mass actually is. And that's what I want to teach you how to do. So what that actually means is finding a way to express the piece of mass in terms of its location. Now, that doesn't make a lot of sense in the beginning, but let me give you a few relatively simple steps. First, we've already identified where our piece of mass is. Now we need a variable that can describe where it is. So start at your axis of rotation and consider a possible variable that could tell us where the start of the object is. I'm going to use x. And I'm purposefully choosing it as a variable that's not written down anywhere yet so that it is different on purpose. So I don't confuse it with anything else. I'm using x because it's horizontal. It's already kind of expressive of the x direction. The other reason I'm using x is because as I look at this, it does look to be along a number line starting from a place that's 0. Now, when I choose a way to point out where my mass is, I need to make sure that the thing that I'm using to point at my mass can be a value that will encompass the first mass and the last mass and all the mass in between. Meaning the value I'm using, x, will it be sufficient to describe where the first mass is? Is there an x that will describe the location of the first mass? I think yes, 0. When x is 0, I'm pointing at the first mass. And is there an x that will point at the last mass? I think yes. When x is L, I can point at the last mass. And is it clear that between 0 and L, I will be able to take in every piece of mass of my object? So we are choosing a variable that can point to any mass on the object, and I've defined where the first object is and the last object. That is step 2. So step 1 is to identify where a piece of mass is. I drew a box, dm. And the second one is to find a way to point at it and to be able to point to every piece of mass with that variable. That's not easy to do. This is one-dimensional. And so I know y'all are looking at me like, yeah, Mr. Shelton, big deal. This is not hard. I know this is not hard. This isn't the one that's hard. This is the test case for the ones that are going to be hard. So the first step, identify a piece of mass. The second step, find a way to point at it and make sure that that pointer can encompass every piece of mass. Now I'm going deliberately super slow. Step 3. Can you describe the size of your piece of mass using your pointer variable? That's a question, but that's what you must answer to complete step 3. Can you describe the size of your piece of mass using your pointer variable? Now to do that, it's not hard. I'm using x to point out where the piece of mass is. If I want to describe the size of this piece of mass, it's a little bit more than x, right? Its length is how I can describe it. So if I say, okay, the piece of mass is located x distance away and its size is delta x, it's a little bit bigger than x. I don't have to describe this portion of its size because it's uniform. It's not getting thicker. It's not getting larger in that direction. So all I have to do is tell you how wide the piece is because it's got one-dimensional symmetry. And that's enough for me to identify the size of the object. And I'm using the variable that is used to point out the object. All right. Now, we won't actually use delta x. I'm writing the delta to remind us that it's just a piece, but we will use the calculus version of delta, and I will use dx. Now, what I really want to do is find the mass of that piece. And I want to do so using things that I know. This is what we just did in preparation for this. Things that we know. I know the mass per unit length of the entire bar. And I know that will have to be equal to the mass per length of the piece. I need to set up a ratio that will allow me to solve for dm in terms of my pointer variable. I'll say that all again. I need to set up a ratio that will allow me to solve for dm in terms of my pointer variable. So I've done that. I can solve this for dm. This is kind of where we ended yesterday, but you guys were not, I don't think, acclimating as well. I had a lambda here instead, but I'm not sure that was working out. So I'm not going to have the lambda there. I'm just going to have my dx and my dm, and I'm going to use the variables that describe the size of the whole bar. All right. Putting this together is probably the hardest part of this. And I know this one, you're looking at it and saying that, well, it wasn't very much, but trust me, this is the hardest part. Because once you have to do this part, the next part is actually pretty easy. The next thing you have to do is assemble the integral. So this is a second set of steps. Our first set of steps really allowed us to replace dm with something about the shape of the object. So that set of steps I gave you to put a box in there, find a pointer variable, because it described the whole size of the object, all of that, that was to be able to get an expression for dm in terms of the shape of the object. That's what I have. That's what this is. Now we're going to assemble the integral. And the integral has three parts. So I'll make this nice and big, but we are going to assemble the integral. We need to put in our dm, the expression we just found for dm. That's going to be m over L dx. We have to put in our variable that we are using to point at each mass. So we're pointing at each mass using x. Because remember, r represents the perpendicular distance from the axis to our piece of mass. And in our picture, x also represents the perpendicular distance from the axis to our piece of mass. So we're going to replace r with x squared. So step 1, replace dm. Step 2, replace r. And step 3, identify where the first piece of mass is and the last piece of mass. The first piece of mass goes on the bottom. The last piece of mass goes on the top. Yep.
For all one-dimensional things, is dm always going to equal m over ldx?
I can't think of a situation where it probably won't. But for all one-dimensional objects is kind of a misnomer. There is only one kind of one-dimensional object, and that's a bar. Every other object is going to be two-dimensional. What's that?
It's not all the same two-dimensional. One for.
Actually, no. We'll find that the thing we create for each of the dimensions ends up being reusable. But wait, let me say that different. The thing you create will be reusable within that coordinate system that it was created for. So if you create one using Cartesian coordinates in 2 dimensions, you will end up with a dx dy at the end. If you create one using polar coordinates instead, then you're going to end up with something that looks like r dr d theta at the end. You're going to have you'll have a d something for each of your coordinate systems. So if you use spherical, it'd be dx, dy, dz. So for 3 dimensions. Does that make sense? It might not, and it doesn't have to. We'll do a 2-dimensional one maybe today, but probably not, because I'm going really like glacier slow here.
With one-dimensional objects, are there going to be any situations where the density is
Yep.
uniform?
We've assumed the density doesn't change here. The last time this was on the AP exam, the shape of the object wasn't like this at all. It was one in which the density did change over the length of the object. And you had to find the moment of inertia of it. It then became the spoke of a wheel that was then used in an angular momentum problem. So, yeah, we're just getting started here. All right. So we have assembled the integral, right? We did all 3 steps. We replaced dm, we replaced r, and we set the limits of our integration. We pointed out the first object and the last object. This will be the moment of inertia of a bar. Now, as I said before, setting up the integral is the easy part. It's the hard part. Executing the integral is like doing your times tables. There is a procedure for doing integrals. Executing the integral is something you're learning in calculus. It does the magic. It does the summation. When we have this, unless you can find a recursive formula, you did the summation. When I walked around and looked at your work, you did it manually. You had mr squared for every one of the dots on the meter stick. Calculus takes that away. The process of doing the integral is going to be doing the sum. It's going to sum it for us. But you don't have to, they're not connected. The process of integrating does the sum. You don't have to actually do the sum yourself. You just have to know how to integrate. Now, integrating isn't magic. It's a procedure. And we only have like 3 different integrals we have to do. This is one we've done before. To make it look like that, let's focus just on what's here and not what it's from. Anything that is a constant can be taken out front of an integral. That's constant. The mass of the whole bar doesn't change, and the length of the whole bar doesn't change. So I can take that out front of my integral. So do. The only thing that actually matters in the entire integral is whatever this variable is. That's our integrating variable. And whatever variable shows up there, that's the important variable. That's the one you pay attention to. So we purposely set this up so x would be the important variable. Chose it that way. Now, we've talked about integrating. This is a polynomial. X squared is our polynomial. We just have to use the polynomial rule to do the integration. Integrating has just a couple of procedures. The first part is to find the antiderivative of x squared. Integrating does derivative in the reverse, so we have to find the antiderivative of x squared. You should remember from how to do this from back in September, but if you don't, we are going to add 1 to the exponent, and we are going to divide by the new exponent. I have found the antiderivative of x squared. It is 1/3 x cubed. Now that that's done, you can't forget that there is a set of variables out front, bring them down, but the integral symbol disappears now because we've done the antiderivative. This function will add up and sum all of the different pieces of mass from 0 to L. To do that, I now must put in my limits of integration. So step 1, find the antiderivative. Step 2, put in your limits of integration. So that simply means to start at the end, put in the L first. So I will have m over L times 1/3 L cubed. You put L in for x, since x was the variable of integration. And then you subtract the lower limit. So 1/3 times 0 cubed. And now all you have to do is algebra. Collect like terms and such. Express your answer. So you notice that one of the L's cancels, right? So get rid of this one. Cancel one of the L's. Collect terms. I get 1/3 ml squared. Now, folks, before you run away, if this were a meter stick and its length was 100 centimeters, that would be 100 squared, which would give you 3333 m. Right? Isn't that expected? So we now know that we're close, but this is exact. This is the moment of inertia of a bar spun about its end. All right. I know that took a long time, but I'm hoping that it will pay in spades when you guys have to do more complicated ones. All right.